Hello folks, this is Jax here with a part 2 of the shift registers video presentation. I apologize for ending so abruptly and without warning on the previous presentation, shift registers part 1. It's just the fact that it seemed a good place to stop. I think if I had carried on to shift registers, I would have probably exceeded the 10-minute allowable uploading time for YouTube. So let's move on. But before we do, let's have a quick recap on what we covered in part 1 of the presentation. We looked at registers, not shift registers, but registers. And registers are used to store bits of binary data. Here we've got 4 D-type flip-flops. We can store 4 binary values. Hence, it's a 4-bit register. Now, clock is assumed to be a common entity to the whole circuit, where this is just particular one element of a complete circuit. So clock is a common entity. However, load and clear lines are specific to these registers. Now, load and clear allow us to transfer data, enter data into and retrieve data from the registers at our own pace. This is exactly what you want to do in memory, don't you? You want full control. You don't want to have to take the data out at a specific time. You want to load it into the memory and keep it there if you want it indefinitely, and then take it out whenever you desire. So load and clear allows you to do this, and I kind of went to some detail on the previous presentation. By all means, if you haven't seen that, I strongly recommend that you see that before you actually continue listening on to this. So we'll continue now on to shift registers. This is a 4-bit shift register, and all it is 4 flip-flops, D-type flip-flops, connected together with the Q's and the D's connected together. Now, the input to the shift register is the D input on the flip-flop to the extreme left. Now, I've loaded this flip-flop with 1, 0, 0, 0, and the output points I've labelled as A, B, C, D. So data is actually inputted using the D input on the flip-flop that's to the extreme left. Okay, now we've got a table there of clock A, B, C, D. It's a negative edge triggered clock, and it's a synchronous connection. So all flip-flops get the clock pulse simultaneously. Initial values for the outputs are 1, 0, 0, 0. Now, assuming that we enter a value for D, what we have is a new value for A. Previous value for A gets shifted to B. For B gets shifted to C. For C gets shifted to D. What happens to the value at D? Well, as far as we're concerned, that value is destroyed. It gets chucked in the bin. Now that's after the first clock pulse. After the second clock pulse, we have 2 new values, and you can understand why I've called it X. I'm not being specific. It's a logic 0 or logic 1, one of those 2. But A, B take on new values. Previous values get shifted to the right, and the one that was on D is now destroyed. Third clock pulse, 3 new values, shifted to the right again by 1 bit. Fourth clock pulse, we have brand new values for A, B, C, D. Previous values are completely destroyed. This, folks, is a shift register. It does exactly what the name says. It does exactly what's on the can. Bits of data are shifted one way. In this particular instance, they're shifted right. One application of this is numerical manipulation of data. Now, we've got the same circuit here, 4 D-type flip-flops connected together. Initial values are 1, 0, 0, 0 for A, B, C, D, respectively. Now, what we're going to do here, the difference is that we're going to assign each flip-flop a binary weighting. How we do that is not important here, but we're going to do it, and we're going to assign the flip-flop at the extreme left a binary weighting of 8, then 4, then 2, then 1. This fits nicely with the binary numbering sequence, which, as you know, the bit to the extreme right is the least significant bit, bit 1. And then it goes 1, 2, 4, 8, and increases by the power of 2 every time. Right, this is a shift right register, and we'll see how it operates on the next slide. Initial values are 8, 4, 2, 1. In whichever column there's a 1, well, that weighting then exists. So, for example, on the initial one, we've got 8 as 1, so that numerical weighting is 8. Now let's have a look at how that actually came about. We've got a clock pulse there. So we have a clock pulse at the top, and this time there's an input of 0. Previously it was for the generalized shift register previously, I'll put it as a X because it could be 1 or 0, but this time I'm going to load zeros into the shift register. Now, initially, the first flip-flop on the left, which was assigned 8, is high. Then after a clock pulse, it's the second one, 4, third one, which is assigned 2, and the fourth one, which is assigned 1. Now, if we look horizontally down, vertically down, at every clock period, then the weighting of the first after initially is 8. The weighting after the first clock pulse is 4. The weighting after the second clock pulse is 2. The weighting after the third clock pulse is 1. Now, in terms of mathematical operation, we've actually divided by 2 at every clock pulse. Now, it doesn't have to be this initial sequence, it could be any sequence. And every time there's a 0 is loaded into shift register, you'll get a divide 2 operation. So, this is one particular application of the shift register. You may want to divide the result by 2. Now we move on to the shift register, but it's actually shown in the reverse order to the one that we started with. Now this time the input D is not the one on the extreme left, it's the flip-flop on the extreme right, and then Q is connected to D of the next one, going from right to left. Now otherwise it's the same. Now A, B, C, D is loaded as follows: D is 1, C is 0, B is 0, A is 1. It's still negative edge triggered and it's still synchronous. Now initially we've got a 0, 0, 0, 1. After the first clock pulse we have a value loaded in from D from the on the flip-flop output that's to the extreme right. Gets shifted right left this time. So 2 values, 3 new values, and after the fourth clock pulse we've got 4 new values loaded into the flip-flop. All previous values have been effectively destroyed. In this register, data is shifted left. Shift left register application for numerical manipulation. Well, same values loaded, same circuit, but this is assigned binary weightings just like our first example. It's assigned the same binary weightings as before because I'm saying consistent with the binary numbering system, which has the bit at the extreme right, which is the least significant bit, and every column to the left is to the power of 2, greater than the previous one. 8, 4, 2, 1. Shift left register. Now initially the binary weighting is 1. After the first clock pulse the binary weighting is 2. After the second clock pulse the weighting is 4. After the third clock pulse the weighting is 8. And then it just goes to 0 after the fourth clock pulse. And we see the waveforms there. Can you see that? So it's 1 initially, 2, 4, 8. Now shifting right divided the data by 2, shifting left multiplies the data by 2. This application should not seem that alien to you because you've seen it in embedded systems where ADC con are 2 8-bit registers and they're combined to make a 12-bit analog to digital conversion result. Because it's an 8-bit processor, the values are going into 2 8-bit registers, and then you are actually combining those registers. But in order to get the right binary weightings, you're shifting left, as I remember. So it shouldn't seem that alien to you. Okay folks, at this point I'm rapidly approaching the 10 minutes for my videos, and what I'll do is I'll finish it and I'll see you in part 3 of the shift registers presentation to look at some specific configurations and some applications of those shift registers. Okay, I'll see you in a bit. Bye bye.